Today we're going to talk about representable functors. Representable functors are particularly well-behaved kind of functors that give us all sorts of useful things afterwards. One thing that we're going to be talking about is the yoneda lemma, which tells us about natural transformations between ordinary functors and representable functors. Another thing that we get out of this is a very nice way of sort of decomposing all pre-sheaves canonically into representables. So the representables are particularly well behaved. We can build up other functors from them. But first let's see what the representable functors are. So let's fix ourselves a category. Then there are two kinds of representable functors. There's the covariant ones and the contravariant ones. And so we have, given any object, A in C, we have the following representable functors. We have the representables they're usually notated with an H, and then there's a terrible difficulty of getting your upper and lower script right. Lower script A, subscript A, usually means that this is a contravariant functor, so it's going to go from C op to set, and what does it do? It's going to take any other object in C, let's say X, and it's going to send it to the hom set. So it's the set of morphisms from X to A. So C has to be locally small to do this. And because X is in the first component here, this is op, because it's op in the first component. We'll see that a bit more in a second. Sometimes the only way to be really sure that you've got your ops and things going the right way, if you're worried about it, is simply to write out all the morphisms. Then you simply can't get it wrong. So let's see what a morphism does here and see if we got it right. So if we take a morphism from X to Y, let's call it F, this has to go somewhere over here. Now what can it possibly do? It's got to be a morphism. We think it's op, so it's got to be a morphism from the set of things, it's got to be a function from the set of morphisms from Y to A. So this has to go from here. Now we've got a slight notational problem, but this is kind of what the function is that we're ending up at. It's got to go to the set of morphisms from X to A, right? Because this is our functor applied to X, and this applied to Y, sorry, and this is our functor applied to X, right? And so what this morphism is, you could call it H sub A of F, but what does it do? How can we take any morphism that goes from Y to A, turn it into a morphism that goes from X to A using this one here? So supposing we're given some morphism here, let's call it S, that goes from Y to A. Now you see why you can get confused, there are just too many morphisms lying around. But let's just draw it up here. If you start with a morphism from Y to A, called S, how could you possibly turn it into a morphism from X to A? Oh, you could pre-compose it by this morphism from X to Y that we've fixed. So that's exactly what we do. This is in fact pre-composition. So what we get is S composed with F. So we can write this function as blank composed with F. And because we're writing our composition in this order, the F lands up looking like it's on the right when it's actually acting on the left-hand component. So we are correct that this is contravariant because we started with a morphism from X to Y, and we produced ourselves a morphism in the opposite direction from HA of Y to HA of X. So this is the contravariant representable at A. Of course, there's a covariant one as well, which we write by an upper script, a superscript. So H upper A, it's now contravariant, which means that instead of having X in the first component of the hom thing, it's going to be in the second component. So this is the set of morphisms from A to X. And now, if we take a morphism from X to Y over here, where's it going to go? Well, it has to go from H upper A of X to H upper A of y. This is c from a to x. This is c from a to y. So now we're saying, okay, if we take a morphism from a to x now, so this helpful diagram isn't going to help anymore. We're going to take a morphism from a to x, let's call that s, and work out how we can possibly turn it into a morphism from a to y given f. Oh, well, there's only one possible thing we could do, and that is post-compose by f. So here we're starting with something from a to x called s, and it is going to be sent to f composed with s. So this is post-composition. We could write that as f composed with blank, and it's the functor h upper A applied to the morphism f. So that's the other representable. Now, of course, there's one of these for every object A, but you might ask yourself whether that in itself is a functor. That is there a functor that sends an object A to this functor? And there is, and that's called the yoneda embedding. So let's just recap what I just said. Given any A in C, we have a functor H sub A, which is in the functor category. So it's a presheaf on C, it's in the functor category, functors from C up to set. And so we can ask ourselves, does this extend to a functor? Does this extend to a functor from C to C op set? And the answer is yes. So on objects, we saw it's going to send A to the functor H lower A. So what's it possibly going to do if we take a morphism F from A to B? Where can it possibly go? Well, it's got to take ourselves to a morphism from HA to HB. But what are these? These are functors, right? So this has to be a natural transformation. This is going to be written H sub F, and it is a natural transformation. As a natural transformation, it has to have some components. So what are its components going to be? It needs a component at every object of C. So the component at X in C, so we've got to have H sub F has to have a component at X, which takes us from this functor applied to X to this functor applied to X. But what are those? Now I feel like I've run out of space, so I'm going to go up here. We're trying to go from H sub A applied to X to H sub B applied to X. Right, but this is the morphisms in C from, and this is contravariant in X, so the X is going over here, from X to A, and this is the morphisms in B, in C, from X to B. So this component has to be a function from this Hom set to this Hom set. And what's it possibly going to be? How can we start with a morphism from X to A and produce a morphism from X to B? We start with a morphism from X to A. How are we going to produce a morphism from X to B? By post-composition with our original function morphism that we had here. Right, so this is going to be post-composition. It's going to send S to F composed with S. So it's going to be F blank. And next time what we'll do is we'll show that this really is a natural transformation. Let's quickly go over what we just did about representables. We started with saying, given any object in a category C, there's a representable functor h sub a that goes from C up to set, which sends A to, no it doesn't, it sends any object x to the set of morphisms from x to A, and then given any morphism f from x to y, what we get is pre-composition by f. Okay, now the next thing we said was that we actually can turn that into a functor from C to the category of functors from C on to set. So we send A to this functor HA. Now we need a bit of notation, so I'm going to call this H blob, because what it does is it takes A and it puts it where the blob is. Now supposing we start with some morphism F from A to B, then what do we get over here? We get something that goes from HA to HB. Right, so this has to be a morphism from HA to HB, and it's called H sub F. And what's its component? Well, a component of this has to go, we've got to have a component of H sub F at X, and it's got to go from H sub A of X to H sub B of X, because this is a natural transformation from H sub A to H sub B. This is the morphisms from X to A, this is the morphisms from X to B, and so what this is post-composition by F. Post-composition by F. Now, we should point out over here that if this is a morphism, F is a morphism from X to Y, then this one goes in the opposite direction. This goes from C of Y comma A to C of X comma A, whereas this one starts from C and ends in the category of contravariant functors. So now what we really need to do is show that this thing here is really a natural transformation, because all I've told you so far is what this thing here, what it has as its components at X. So we started with a morphism here. We wanted to produce a morphism here. What are the morphisms here? They are natural transformations. We've defined our natural transformation component-wise. Now we've got to really show it's natural. So what would naturality say? So this has to be a natural transformation in here. So we've got to be careful about our ops again. Let's just draw out a generic naturality square for this. It would say, given any morphism, let's call it G, from X to Y, we've got to have a naturality square that looks like this. So we're going to have HA of Y going to HB of Y at the top via the component HF at Y. Then down here we've got to have HA of X going to HB of X via the component H of F at X. Now coming down here, we've got H sub A, the functor applied to F, G. G goes from X to Y, so when we apply this contravariant functor to it, it goes in the opposite direction. And similarly here, this is going to be H sub B applied to G. Right, now let's see if this thing commutes by writing it out a bit better. This top left-hand corner is H sub A of Y. So this is the morphisms from Y to A. Here we've got the morphisms from Y to B. Here we've got the morphisms from X to A. And here we've got the morphisms from X to B. Right, now let's see what the morphisms in this square are. This top one is going to be this component of the natural transformation, so that's F composed with blank, and so is this one. Coming down the sides, we're applying this to a morphism, so that's this one, so it's composition on the other side with our morphism G. And now we can see if this actually even type checks, because we're going to start with a morphism from Y to A. Let's call it S. We're going to send it over here by composing it, precomposing it with F. Okay, F goes from A to B, so we're going Y to A to B. That is a morphism from Y to B, and now what happens when we come down here? We're going to turn it into a morphism from X to B by composing it on the other side with G. X to Y to A to B. So here we've got G, here we've got S, and here we've got F. Now I hope you're beginning to see what's going on here. If we come down this way, we're going to compose with G first, so we get X to Y to A, that's G followed by S, and then we come along here and we'll get X to Y, and we're going to post-compose now by F, X to Y to A to B, so this is G, S, F. Now of course what's really happened here is here we did the S and the F part first and then did the G part afterwards. Here, we did the G and the S part first and did the F part afterwards. So this naturality square is actually telling us, is actually the same fact as associativity of composition in the category. So the fact that this is a natural transformation is the fact that composition is associative. So really nothing at all has happened. You should feel like really this is a very, very kind of fundamental natural transformation. It's just capturing one of the most basic axioms of a category, so it's almost completely content-free. It's very, very fundamental. And in fact, this is called the yoneda embedding. So this is called the yoneda embedding. And it tells us that we can embed a category inside the category of presheaves in a very nice way that looks a bit convoluted, but it gets faithfully embedded in here. We can't prove that yet, so I've called it the yoneda embedding without actually proving that it's an embedding. In order to do that, one thing we can use is we can use the yoneda lemma. So the next thing we're going to do is talk about the yoneda lemma. We're now finally ready to talk about the actual yoneda lemma. Now, the yoneda lemma is something that compares the representable functors with random other functors. Well, not completely random other functors, because of course, if we're looking at the representable functor that goes from C op to set, what we're going to do is we're going to consider the situation where we have another functor, and not necessarily representable functor going from C op to set, and a natural transformation there going like that. Now, if alpha is actually a natural isomorphism, then we say more generally that F is representable as well, although it's not actually one of the representables. But that's not what we're going to talk about here, although if we're lucky, we may talk about that later. We're just going to talk about natural transformations like this, because as it turns out, these are very, very closely controlled. There's very little that they can do, and they're completely controlled by a very small amount of data, which means that, well, we can say the yoneda lemma. And there are often, the situations where we use it are often situations where you think that there's lots going on, where in fact it turns out you have very little choice of what's going on, and everything that's going on everywhere is just controlled by one really small thing. So we'll see what that means in a second. So what's going on here? What it says is that a natural transformation here to here, well, let's see, what's the natural transformation from there to there look like? We're going to consider natural transformation alpha that has as its components, well, it's got to have components that go from HA of x to f of x. Okay, and so what's this? This is the common things in C from X to A. And the point is that there's a very special thing inside all of these possible things, which is in the case, if we put X equals A, then we get the common things from A to A going to f of A. So this is the component A sub alpha. But of course there is an identity in there. And the idea of this is that the identity goes somewhere. Where? Well, it goes to there. And that this actually determines the entire rest of this natural transformation. So once you know where this identity goes, you know where everything else goes. So let's just informally have a look at why that could possibly be true. So supposing we know where this goes. Now we want to know where that goes. So we want to now work out what the component at X is that goes to f of X. So what we do is we can start by looking at a naturality square, and now I'm desperately hoping that I've got my naturality square the right way up. We want to know where some morphism f from X to A is going to go, right? That's what we want to know. And what we know is we know where the identity goes. So I've declared that once we know where this goes, we know where everything else goes. So we know where that goes. So now what's this naturality square going to tell us? Well, we have a morphism coming down here and a morphism coming down here, because we're trying to work out where this f goes. So we can, once we're told which f we're trying to consider, we've got an f, right? And it goes from X to A. So this f of f is going to go from f of A to f of X, okay? Because f is a contravariant functor, and this here is going to be pre-composition with f. So now we have a naturality square. What does it tell us? Well, going along the right-ish, the top right leg, if we start with the identity, it goes over here, and it comes down here to f of alpha A 1A. Okay? Now where does it go when we come down here? We come down here and we compose it with f. So the result of coming down here is in fact f, as we wanted. And so we know by the naturality of this square that when we go over there, we've got to land in the same place that we first came up with. So look, we know where it is. It's got to be equal to that. So the result is that once we know where the identity went, once we knew where the identity went, we could tell exactly where every single other thing went. So this is not a proof, but this is basically the entire idea of what's going on. Of course, one of the reasons it's not a proof is because I haven't actually stated what it is we're trying to prove yet. So why don't I do that now? I'll leave that up there for a second and write up what the yoneda lemma is. The yoneda lemma says that there's an isomorphism. So what was it an isomorphism between? Well, what's this? This is just an object in f of A. Okay? So somehow we said that things were completely uniquely determined by some objects in there. And the thing that we started with was a natural transformation from here to here. So we're looking at the totality of natural transformations from HA to F. And what we're saying is that the natural transformations in here precisely correspond to just elements of f of A. I didn't quite say this, but once you know where this goes, you know where everything goes. But moreover, this identity can go anywhere. Okay? So that means that not only is everything uniquely determined by where it goes, but there is one for every possible place that that identity goes, which tells us that there's a bijection between these two things. Now, of course, in category theory, we don't like staying with bijections. We like things to be natural isomorphisms, and the naturality says that this isn't just any old bijection. It's a sensible one that was somehow induced canonically by some nice structure. That's what you should think when you think of natural isomorphism. And here it is. This is the canonical way that the thing was induced. It wasn't just some random correspondence between things over here and things over there. It was a really nice one that was induced by composition with something. That's often what the naturality is saying. So what this is it's a natural isomorphism between here and here. Natural in what? It's natural in everything it could be natural in. It's natural in both the object A and F. So it's natural in A, so this is as an object of C, and it's natural in F as an object of C offset. That's probably an op up there. So, to recap again, it's saying that any natural transformation in here is completely determined by an object in here in a really nice way. So what we'll do next time is we'll actually completely prove it. It's a nice exercise, if you like that kind of thing, in pure diagram chasing category theory. You should be able to go home and do it yourself now. So perhaps in between watching this and the next video, you can go home and do it yourself.